to go ahead and get started. Thank you all for coming. This is, you can already tell, DevOps KC Meetup, and glad to have you all here. This is your first time? Okay, good. We tend to have about 50% people show up that have been here, that have not been before. The fact that that doesn't mean we continue to grow by 50% means we must be doing something wrong because people don't come back. They actually do, but because the other 50 are here. We just need to get everybody coming back at the same time, and then hopefully show some company that wants to sponsor, $1,000 worth of food. Anyways, if your company wants to sponsor, let us know. Anyways, yes, I'm Jeremy, one of the core organizers for DevOps KC Meetup and for DevOps Days KC. Good to have you all here. Kind of thing, we've already done the food. We're going to have our sponsors real quick. Tech Systems, you want to come up, Alyssa? Come and give a little spiel about who you are and what you all do. And,
me specifically?
Yeah,
Tell
I go for that too. Yeah.
I know he went around and asked who all has been to a DevOps KC event before, but who all has heard about Tech Systems before? Yeah, some familiar faces out there. Well, if you don't know who Tech Systems is, we're one of the leading IT staffing and services companies here in Kansas City. I primarily support our digital space, so everything from healthcare to retail to agency. DevOps is a little bit outside of my wheelhouse, but it's always really fun to kind of get connected to the other folks who are also a part of the community here in Kansas City. If you guys have any questions about events going forward, any questions about Tech Systems, I'm here. My gal pal Rachel is back in the corner too, so if you guys are looking to get connected to a recruiter or an account manager, or aid in your job search, or just kind of see how the market is doing, would love to get connected with you guys afterwards.
Cool. Yeah, thank you very much. And definitely, like Alyssa said, get with them. And if you're not looking, you probably know someone who is. So definitely kind of take their information, say hi. They're going to pass a little note thing just to sign up so that they know who all's been here and that. So cool. Well, the other thing, Confluent, who Chris is going to be speaking in a few minutes. He's with Confluent, but Confluent is sponsoring the food and drink that we have. So, thank you to them. Go definitely check them out online. And we'll be posting some things about that soon. Let's see here. All right, so we usually kind of do this thing where if anybody has kind of an announcement of something happening in town in the near future that they are kind of interacting with, that they kind of enjoy, that they want to get people out there, now's the time to kind of just speak that out and just kind of tell everyone what they got going on. Anyone else? Brian, I guess.
I bought my ticket to the DevOps Days conference.
Really? I think we have some more info about that too. Everybody should, we'll have some info here in a minute. But yes, I mean, DevOps Days, who here has not bought a ticket?
It's coming back this year.
That would be everyone that has not bought a ticket yet. We just kind of rolled that out, so I'll have a little bit more on that. But yes, that's a good call out. Any other things happening around that you want to kind of call out you're kind of working with?
JavaScript KC kicks off their first meetup tomorrow.
Yes.
It's at the North Garden lobby? Question mark? I will confirm.
Yes.
That.
But it is on Meetup. It is on Meetup.com as well.
Yes.
And so definitely JavaScript KC down at Garmin tomorrow. Definitely check that out. Who else? Who has any other kind of announcements of things they're doing?
Python KC's having their winter meetup, the Keystone collab out in KC.
Okay.
And that's on Thursday.
So this coming Thursday. So this Thursday, Python KC. Is that on Meetup.com as well, or is it? Okay. So perfect. So Python KC, another good meetup to get involved with. Is what's the time on that? Do you happen to? Okay, check it out. Probably it's on Meetup.com. Python KC. That's this Thursday. Anything else? Any other kind of meetups or community things happening? Okay, cool. Next, we're going to have Chris. He is a solutions engineer at Confluent. and Chris is going to talk to us about some common event streaming patterns. So with that,
All right, well, good evening, everyone. My name is Chris Harmon. I am the solution engineer with Confluent, and tonight I'm going to be talking about some common principles and design patterns that you should think about when you're designing real-time applications using data streaming platforms. Naturally, this being a joint meetup with DevOps KC as well as the Apache Kafka Kansas City group, the focus is going to be on Apache Kafka this evening, but many of the patterns I'm going to be talking about, they're not specific to Kafka. They can be applied with any other event streaming technologies as well. For anyone who's not familiar with Confluent, we were founded in 2014 by the original creators of Apache Kafka, and our engineers are still very active in the open source project. We account for over 80% of the commits to the open source Kafka project, and we're very active in the community as well. So today I'm going to cover some of the most important and commonly seen patterns that folks are using, but it's by no means going to be exhaustive. You'll be able to find some more info and more examples about these patterns and many more over on the Confluent developer site. That's the Confluent developer site. It's a great resource, especially for folks who are new to Kafka, new to data streaming concepts in general. So I definitely encourage you to check that out if you haven't already. A lot of these patterns I'm going to talk about, like I mentioned, they're applicable regardless of what messaging or data streaming platform you might be using. But we are specifically going to be talking about them in the context of Kafka today. So if you're new to Kafka or you just want to learn some more about it, definitely go check out Confluent Developer. Also, on Confluent Developer, you'll be able to get access to the Confluent Community Forum and our community Slack, which are great places to just reach out to the community, get help, answer questions, that kind of thing. So a super quick intro. I'm not going to get into technical internals, but just for folks who may not be familiar with Kafka, what is it? What does it do? Why are we talking about it? Well, Apache Kafka is a distributed immutable event log. It can process streaming data at really high throughput, really low latency, and store that data durably for as long as you might need. It's going to organize data into topics. You're going to have data producers that write data to a topic and data consumers that read data from a topic. And the really cool thing about Kafka compared to other queuing or messaging technologies that you might have been familiar with, messages are not going to get deleted from the topic as consumers read them. They stay in the topic, they're durable, and other consumers can come and read the same messages whenever they want independently of each other. Those messages will stay there until they get cleaned up based on whatever retention you've specified for that topic. And like I just touched on, your data producers and your data consumers are fully decoupled from each other. The producers don't know anything about the consumers and vice versa. They don't need to. They're completely independent by design. And then, like I alluded, different consumers can read the same data from the same topic, but independently of each other, and even from different points in time in the same stream. So that opens up some really powerful use cases beyond just simple messaging between microservices or real-time ETL data ingestion kind of scenarios. Because those events are getting durably stored in Kafka, that lets us also have the ability to replay them from any time we want at any point in the stream to do something like reprocess a data set. Say I have like a bunch of events and I want to run up against my pricing model and I made some changes to the model I want to A/B test. I can use the same data that I trained the original model on and see if I get different results with the new model. So a lot of companies, from digital native startups all the way to massive multinationals, are using Kafka as the backbone for their entire enterprise. If you got your data flowing through Kafka, and in a lot of cases even beginning its life cycle in Kafka, then you can write that data once and then effectively broadcast it out to all the downstream systems that need it. And then we've also got, on top of the core Kafka topic semantics there's stream processing technologies that build on top of it, like the Kafka Streams API, Apache Flink, which is becoming really, really popular these days. That let you do stuff with that data while it's in flight, enrich it, transform it, join different streams and external tables together, and that kind of thing. So that gives you a high-level idea of where Kafka fits in an enterprise data architecture and how data flows into and out of it. The most obvious way you're going to get data in is through applications that are using the producer API to just send messages to a Kafka topic. And that could be any kind of data. It could be click events on a website. It could be financial payments. It could be video game telemetry, real-time location data from your Uber driver, IoT sensors, anything you can imagine. The only thing we're generally not going to be talking about when we say data streaming in the context of Kafka is streaming media like audio and video. It's not really optimized for event payloads more than a handful of megabytes in size. Now, once your producer's written some raw events into Kafka, it doesn't just have to flow through to the target system like a dumb pipe or a message bus. We can do stuff with it in the middle. We can enrich and transform that data on the fly, and even do things like build up a stateful view, aggregations that stay updated in real time. And we do that with what we call stream processing. So like I mentioned, Apache Kafka ships with the Kafka Streams API, which is a Java library that lets you do that kind of stateful stream processing. We've also got ksqldb, which is like an abstraction layer on top of Kafka Streams that gives it a SQL API. So if you're not a Java developer, you can still kind of leverage Kafka Streams for your applications. And then there's also Apache Flink, which is another really popular top 5 Apache project that's kind of emerged in recent years as the de facto standard for stream processing. And you're going to be hearing a lot more about that in the very near future, both from us and just in the community at large. It's really what everybody's looking to these days to do stream processing at scale. And then we'll have applications that are consuming those streaming events from our Kafka topics. So again, these different consumers can all be independent from each other. They don't affect each other. They don't have to know about each other. They can each read and replay events however they need to, whenever they need to. Kafka gives us really strong durability and delivery guarantees and can support at least once or exactly once delivery semantics for that end-to-end delivery of your message from the producer end to the consumer end. And you need to be careful with the consumers, and ideally, because they can replay those events from the Kafka topic, you want to try to design them to be idempotent so that if you need to reprocess the same data, or like let's say your consumer fails and it has to reprocess the batch that it fell down in the middle of, you can make sure that you end up in a consistent state downstream. Sometimes we might have some existing data, going besides just an application that I'm making right to Kafka. I might have some existing data in an existing database, but I want to get it moving. I want to make it available in Kafka so that other things can leverage it in real time. And so for that scenario, Apache Kafka gives us the Kafka Connect API. It's a plugin-based framework that makes it really easy to get external systems hooked up into Kafka without having to write code yourself to do it. So you can usually find a pre-built connector for a particular database or SaaS system that you want to connect to, and then you grab that, pass it some configuration, and you're off to the races. Of course, all of this is going to have a Kafka cluster at the center as its beating heart. Kafka itself, it's a distributed system. It's designed from the ground up to work with data in motion instead of data at rest like traditional databases. And the topic data in Kafka is going to be replicated across multiple nodes in your cluster. And so you get that extra durability and fault tolerance. So disks fail, servers go down. You don't jeopardize the integrity and durability of that data. And it also makes it really easy to scale Kafka to handle larger workloads because you can just add more nodes to the cluster and scale out. Then lastly, like I mentioned, the Kafka Connect framework, it's not just useful for getting data from sources into Kafka. You can also go the other way. You can use what are known as sync connectors in the Kafka Connect framework and take data from Kafka to push it to an external target system. And again, no code necessary to do that. You just get the appropriate connector plugin, pass it some configuration. So if you want to stream data, for example, into Snowflake, you don't have to bother about taking the time to learn the Snowpipe API, the Snowpipe streaming API, write your code to do that. Snowflake makes a Kafka connector, get that, and just give it the right configuration for your Snowflake cluster. So now we've caught up on some of the basics around Kafka, let's dive in and start talking about some of the ways that you might want to design event payloads that you produce to Kafka for a variety of different use cases. Kafka itself doesn't care what your data looks like. It's just a binary log. You can send it whatever binary data you want. You have complete control over the structure of that payload. So that does mean you need to put some thought into it. You need to put some thought into what the payload should look like based on your particular use case, and then what your downstream consumers are likely going to need for their use case. And when we talk about events in the context of Kafka or a data streaming system, events just record that something happened in the world. thinking about data, data doesn't just pop into existence out of nowhere, right? Something happened to cause a state change in the world. You know, you might, a customer record doesn't just exist. A customer went onto the website and filled out a form and clicked a button at a particular point in time. An order doesn't just exist. The customer puts some stuff into the shopping cart, click the checkout button at a particular point in time. So thinking about also downstream in like a data warehouse, or customer dimension in the data warehouse doesn't just exist, right? It represents the cumulative state changes over time that happen to that customer to get it to what it looks like today. So we can use events in Kafka to kind of get to all of those things. A message in Kafka, or an event in Kafka, is going to consist of 4 parts. It's got a key, it's got a value, it's got a timestamp, and it's got headers. The key and the value are really the meat and potatoes of it. The key typically is going to be what you use to identify some unique entity in the real world. That could be like a database record, it could be a particular IoT sensor, it could be a particular Uber driver, that kind of thing. Kafka is going to guarantee that all the messages for a particular key get delivered in the same order to all the consumers every time. So we've got very, very strict, very rigid ordering guarantees on a per key basis. So as a general rule, you're going to want to keep that key simple. Keep it like a simple string or an integer. It doesn't necessarily have to be. You know, Kafka is just going to take binary data for this. So your key could be, if you need it to be like a JSON object, Avro schema, it could even be a cat picture if you were going to be silly, but there'd be no reason to do that. Kafka is not going to care. It's just a binary walk. But because we're using that key to determine how we balance and shard that data across the cluster and enforce those ordering guarantees, we want to keep it simple so it's easy to understand and easy to work with. Then the value of the Kafka event, that's your main data payload. That's where you're going to put all the data of interest. And again, it's going to be up to you to choose how that's formatted. Kafka, you can put whatever binary data in there you want. The most popular serialization formats that we see people using are things like JSON, Apache Avro, Google protocol buffers. Our record in Kafka is also going to have a timestamp. That's going to tell us when that happened. By default, that's going to be the wall clock time of the producer application. That's what most people will stick with, but there are scenarios where that might not work for you. So you can specify the timestamp specifically yourself, or in some scenarios you can configure that to be the time at which the broker received the message on the broker's wall clock time. More of an edge case, but you have some control over what that timestamp represents in each message. And then lastly, there's headers, which let you add some arbitrary metadata to that event. So you might want to describe something about like the provenance of this event, where it came from. You might need to communicate some information downstream to the client to tell it how to decrypt an encrypted payload. Those are kinds of metadata that would make sense to put in the header of your Kafka event. So a really common use case for event streaming, and probably the one most people are the most familiar with, is decoupling microservices from each other. So you can have one service that needs to talk to another one and send some command to it to tell it to do something. And then that service that gets called, it might need to respond back to the calling service with some kind of acknowledgement or result of the computation or something. But we can do all that asynchronously and without those two applications needing to be coupled to each other at all by leveraging Kafka in the middle. Application A can send its command into a Kafka topic, and then it doesn't have to wait for an acknowledgement that application B has received that message. It can just trust that I know this has been durably written in the Kafka topic. I know application B is listening to that. It'll get to it eventually. And then that kind of helps you make the whole system more fault tolerant, because then if the consumer end, if application B has some kind of a problem, let's say it's running in the Kubernetes pod, you can just shoot it in the head, and when it comes back up, the consumer group protocol of Kafka is going to take care of making sure that it picks up where it left off, gets any messages if it was in the middle of a batch, reprocess that batch, and get back to a consistent state and make sure all of those messages get processed. But like I said, if your application A needs to have some kind of response back from application B, then you can flip that around, and application B can simply drop that message on another Kafka topic that application A is consuming. And they stay decoupled. Doesn't have to, neither one needs to know that the other did or didn't receive the message. They can just assume it will eventually because it knows it's been durably stored in the topic. Now, as events flow through the applications, and especially as we start getting into stream processing scenarios, where we might have several intermediate processing steps along the way, it gets really important to be able to trace a particular event back to its origin, or be able to follow events that are related to a particular logical business transaction all the way through the topology. So to do that, we can add a correlation identifier to the event payload. And that you can kind of think of it as a tracer that will let you follow an event and then any subsequent related events all the way through the topology. So it gets really useful for troubleshooting when something goes wrong in the middle of some kind of a stream processing layout. Like, let's say you know that application A produced a certain record, but then downstream application B never received it. Well, what the heck happened? If I have, maybe a Flink job in the middle that's doing some transformation of the data in the middle, I might not know. There could be several steps in that, and it'd be tricky to find out exactly where things went wrong. Or let's say on the consumer side, my consumer gets a badly formed message out of a Kafka topic. You need to go back to the development team who owns the producing application and say, hey, find in your logs what happened with this message. They're going to have a hard time doing that if they can't track it down. So having that correlation ID in the message will give you something like, hey, I know this specific correlation ID. Go find that in your logs, and they should be able to find everything relevant that happened on their end. Sometimes you might have to pass events between a couple of different systems that really vary quite a bit in nature and have different expectations for the data they're going to receive. And it really doesn't kind of make sense to publish the different kinds of events to different Kafka topics because the order of those events relative to each other still matters very strongly. So it can make it hard to define like a one-size-fits-all schema for that topic's events. So one way we can address that is wrap an envelope around the message that kind of helps us communicate to the consumer downstream what the payload looks like and how to interpret it. So on the producer end, we can add some metadata as a wrapper around the actual event data. Then that gives you some added flexibility as far as how the data payload itself is structured and how it gets handled by the receiving applications. So now that we've seen a few basic things about how events themselves might be structured, let's take a look at some patterns for how events get produced to and consumed from Kafka topics. As I've already mentioned, the real power of Kafka comes from how it fully decouples your data producers from your data consumers. Your event source, or your producer, is continuously producing events to topic. Kafka is appending them to the end of that immutable log. So we know our older events are never going to get changed, they're never going to get deleted except by that background cleanup process. So because we have these events stored durably in Kafka, any number of different applications or sync connectors can be consuming from the same event stream and doing so completely independently of each other, and even potentially from different points in the stream if they need to. All that communication between our producers and our consumers is going to be completely asynchronous and indirect. We usually are going to have some kind of a validation in the middle of the message formats, and we typically do that by a schema registry, storing a data contract for how the producers and consumers can expect that to look. We'll touch on that a bit more in detail later. Generally speaking, this event stream is going to record the history of what has happened as some sequence of events. Like when you think of a sales ledger, you can think of like a sequence of moves in a chess match. Because we have this history as an ordered sequence of events, I know specific events happen in a specific order. I can infer causality. I can know which piece moved where on the chessboard and replay the entire game by replaying all those events in the right order. And so the stream is, it represents the past and the present. We can also kind of infer the current state if we have enough events stored on the topic to do that. I touched on connectors briefly earlier. This gives us a high-level view of how our source and sync connectors work within the Kafka Connect framework. Very frequently you're going to have data stored at rest in some traditional database, like Postgres or Mongo, but the business wants to be able to take some action in real time as the data changes happen in that database. Databases have had their own ways of dealing with this for a long time. Triggers have existed forever in a lot of SQL databases. You can use those to keep objects in the same database, updated in real time. They add a lot of overhead to the database, though. They can cause locking and blocking issues, and you really don't want to try to make them do any kind of remote service calls, even if you can maybe technically do that with your particular database platform. Batch processing jobs, are also usually kind of common for scenarios where you're trying to look at changes since the last time this job ran and figure out what row they need to operate on. It's kind of how a lot of traditional database folks like myself back in the day have tackled that problem. But that's not really great either. That kind of batch-oriented approach usually involves running a really complex query every time you run that job to identify those rows that have changed since the last time you looked. And that can be kind of an expensive operation. And then you're also going to be hard-pressed to get that scheduled more than about once a minute or so if you want to make it an automated process. So instead, we can leverage change data capture on our source database and get it continuously emitting a stream of change events as the inserts and updates and deletes happen in our database. And then we can use a source connector in Kafka Connect to subscribe to that CDC stream and take those change events and produce them as events to Kafka topic. And then from there, we can do processing on them in real time if we need to transform those or join them together to create a denormalized view, and then use a sync connector downstream to send those events down to whatever target system they might want to go to, or any other application that needs to consume that can consume it independently. And we can do all of that without adding any significant overhead to the source database. So the only overhead you're going to have to deal with is whatever background process your database uses to generate that change stream, and then a little bit of overhead from the client reading that change stream. And there's also going to be a lot lower latency than if you try to implement that with a batch job that at best you might be able to get running every handful of seconds. So in that way, CDC is also going to be really useful if we want to migrate our application's data architecture away from being tightly coupled to some particular database platform. So a lot of people are looking at migrating their applications off of a legacy database or off of a mainframe. But the business wants them to start delivering some kind of real-time feature sooner rather than later. And re-architecting that source application that creates the data and writes it to that database often is a really expensive and costly proposition. It can take a lot of time, there's a lot of risk involved in it. So instead of trying to tackle that whole thing up front, what we can do is leverage CDC against that source database to get those insert, update, and delete actions flowing into a change stream that we can then use, and working with those in real time, we can start peeling off bits of functionality from that legacy application on the consumer side. And then over time, we can work on evolving or replacing that producer application. And then once we've got to the point at the future where the source application is rewritten to emit events to Kafka directly, we can just cut the old database out of it at that point. One of the main benefits you get from adopting an event-driven architecture is it really helps foster better collaboration between your application teams. One aim we've got is we want to make sure that Team A can produce data, Team B can process it, Team C can report on it, anybody can do what they want with that data. But with the only thing coupling them together being the data itself, no other application dependencies. Teams shouldn't have to agree on sharing, everybody using the same programming language, everybody using the same libraries. They shouldn't have to synchronize their release schedules or make sure they're all using common tooling. We just use the data itself as an interface between these teams. But in reality, every team is still going to have to talk to that streaming platform, the Kafka topic themselves. So how can we kind of maximize access to that and make it easier for everybody to use that streaming event store, but without insisting that they choose from a short list of supported languages and libraries? Well, we can solve for that by putting some kind of an event gateway in front of it that provides us a standardized, well-supported interface that will give access to the widest possible range of users. A really common way to do this is to stick some kind of a REST proxy or build a REST API in front of your Kafka clusters. For an example, Confluent provides a REST proxy that gives you a broad set of REST APIs that'll let you use any language or a CLI tool that you can issue REST commands with and be able to produce and consume from Kafka. And you can also do that in the various serialization formats that are most commonly used in Kafka. So if you need to produce JSON or Avro or Protobuf, you can do that through the REST proxy also. So that makes it really easy for developers who are using any language to get started interacting with streaming data in Kafka without having to change the programming language you use, learn how to use a new library. They already know how to talk to REST APIs. They can get talking to Kafka as well. All right, so we've had a look at what event streaming is, what events are, and some of the ways of getting events into and out of a streaming platform like Kafka. So let's look now at some of the common patterns for working with those events in the middle and processing them on the fly as they're flowing through a streaming platform. So once we've got our data like financial transactions or maybe tracking information for shipments or IoT sensor measurements, that kind of thing, we get that in motion as a stream of events. We're going to need to put that to use somehow and actually get some value out of it. So how are we going to do that? We're going to use some kind of a stream processor in the middle, which is going to be a component that's going to read some events from our input stream, process them in some way, and emit new events to another topic with the results of its processing. That stream processor itself, may be acting as a source or a sink for some other stream or application, and usually it's going to be doing some of both. The stream processor itself is often going to be distributed with multiple different instances running on different hosts, so we get some parallelism and scaling and fault tolerance with a stream processor in a similar way we do with Kafka itself. The really important characteristic of stream processors is composability. We're seldom going to have a single stream processor operating in isolation of the data. We're usually going to be connecting two or three or more of them together, where one processor takes some action and it's some result to a topic. Another processor takes that topic, does some more with it. A third processor might be joining the results of two different topics together to make a third, and kind of build up like a DAG of different processors working in concert with each other to meet the overall business logic of your application, or solve maybe a small part of the domain problem for a larger microservice architecture. Each processor is going to be performing a specific task within our broader stream processing topology. So some things you might be using a stream processor for, like we might want to filter out only certain events that we care about from an event stream. We might want to enrich a particular stream with some additional data from another stream or maybe an external database table. We might want to use them to trigger alerts in some alerting API, or just generally build up some new kind of event for a downstream application to use. And like I mentioned, we're very seldom going to have just one stream processor operating on a stream. We're going to chain usually several of them together to arrive at our desired final output. So let's say we're working with customer data, we might first need to build up, if I just got an input stream of all the customers as they're getting created, as their addresses change or whatever, the first thing I might need to do is build a stateful view of the most recent version, the most recent thing I know about each customer record, based on all those changes had over time. And once I've built up that stateful view, you can think of it as like a customer table that's just getting dynamically updated. Then I can take that and I can join it to my orders stream, so I can enrich it with all the information about the customer who placed that order. And then if I need to send that to a data warehouse, I might have a third stream processor that will take that enriched order stream with the customer data and aggregate it to give me daily total orders per customer. And I can then take that and send it downstream to my data warehouse and keep my data warehouse customer dimension updated in real time, instead of having to rely on some batch process to come through afterward and do that on an hourly or daily schedule. But meantime, I might have some other application that cares about the raw disaggregated orders data. It wants to be able to see every order, but it wants to be able to see that order enriched with the customer data. Well, I've got that stream in the middle where I've already done that, so this other application can just hook into that intermediate stream and use it for its own purposes without me really needing to do anything special to support that. We might run into some scenarios where we've got a subset of events that need to get processed in isolation for, like, maybe I've got an inventory system that different kinds of stuff flowing through it needs to be sent downstream to some different different application depending on what type of inventory item needs to check. So with the stream processing framework, I can watch those events that are coming from the input stream and then make a decision based on each event about how it should get handled or where it should get routed. So, like, for example, here I've got one stream processor that's taking the dark blue events and sending them to stream A. I've got another one that's taking the light blue events and sending them to stream B, and a third that's taking the yellow events and sending them to stream C. And now if I've got an application that, say, it only cares about the yellow events, that application doesn't need to implement that logic to filter them by itself. All it has to do is watch the yellow event stream, and it gets only what it needs. In a reverse kind of scenario, we could have multiple input streams that we want to merge together to provide a single output stream for some other downstream application. So here we could use a stream processor to basically kind of union or zipper merge those events together from all the source streams and emit one single stream downstream that contains all of the events from both or multiple topics. Because of the ordering guarantees I mentioned in Kafka before, the events that came from stream A are going to stay in the same order relative to each other that they would have in the original stream A in that downstream combined stream. And the same thing for stream B. Like the stream B events relative to each other will still be in the same order in the combined stream. But Kafka does not provide ordering guarantees across multiple streams. So the events from like A and B relative to each other in the downstream unified stream are not guaranteed to be received in the same order as, say, if you had a consumer application directly watching both of the source streams independently. So just be aware of that. Quite often, we're going to have a scenario where the data model of our producer application and the data model of our consuming application are going to be quite different from each other. So I need to find some way that I can move data between very different looking domain objects in two different applications, internal data models, but still have them available on my streaming platform and kind of make them available in a way that's not really married to the domain model of either of those applications. So I want to kind of democratize this a bit and make it easier for other future applications to consume. So we could use an event mapper pattern for this. And what that's going to do is give us some extra independence between what the data model internal to each application is versus what we're storing in our Kafka topics. And then neither of these applications really need to be aware of each other's data model when we do this. So we'll want to come up with some kind of a more generic application independent data model, use that to model the event we produce the Kafka topic. And then in our producer application, we'll have an event mapper class of some time that takes the internal data model of that application, translates that into the common model in one, our streaming topic, and produces the event. And then on the opposite end, on the consumer side, it'll have an event mapper class that, as it receives events from the topic, translates those into its own internal data model and does what it needs with it from there. But we've kept it cleanly decoupled, and nothing about those two applications knows or needs to care about how they're internally modeling that data. So earlier I mentioned, how when we say data streaming in the context of Kafka, we're not really talking about the same thing as media streaming, like video and audio. Netflix does use Kafka really heavily, but the video and audio don't come through Kafka. What they're getting is like lots of metadata about what you watched, when you watched it, how long it took you to watch it, did you use subtitles or not, that kind of thing. That is flowing through Kafka. Sometimes we are talking about moving media around, sharing large payloads, more than a couple of megabytes, but we really don't want to directly use Kafka for that because it's just not optimized for sending large payloads. There is the ability to do compression. So if we have maybe some larger message, like a couple of megabytes of JSON, for example, we could leverage some compression on the producer side to get that down, but that may not be enough in some of these cases. use cases, especially involving any kind of like image recognition, video analytics, audio transcription, where you've got media you need to move around, you're not going to want to throw it through Kafka. But rather than putting the media itself into a Kafka topic, you could take that media object, write it to a really cheap object storage like S3, and then pass a reference to the object, like the S3 URL, in your Kafka event payload. And we call that the claim check pattern, because it really works very much the same way as like checking your luggage for an airplane flight. Like you're not going to carry your giant, I'm going on a 2-week cruise suitcase onto the airplane. There's just no room for it. So you're going to go to the baggage claim agent, you're going to check your bag in with them, and they're going to give you a ticket back that you can use to retrieve your bag at the other end of the trip. Fortunately, though, for you, both Kafka and S3 have significantly better reliability for this pattern than most airlines do. Now, we also might run into some problems with our stream processing application. Sometimes you might encounter some invalid data as a consumer is operating over this infinite stream of events. You might get some nonsensical values, and missing or corrupted values. Any number of technical things could go wrong and cause an unexpected result for your consumer application. So what we can do about this? How can we make sure that our stream processing applications don't just die when this happens? We handle that failure gracefully without crashing or getting stuck. So we can do that by taking that bad event and republish it to a dead letter stream, or you might also hear the term dead letter queue thrown around. Kafka is not really a queue in the traditional sense. It's still the terminology you hear used a lot. But we can take that bad message, put it in the DL queue, and allow it to be logged or reprocessed, or some action can be taken on it later. We can actually also provide some more context with that as well. We could maybe embed the exception message that our application threw into the payload that goes in the dead letter queue, or anything else we might know at the time of erroring that out about why it went wrong. We can enrich that message and put it in the dead letter queue to help troubleshooting be easier later. And in that way, even though we might have some individual events that don't get all the way through to our consumer, the consumer itself can still kind of just gracefully keep going and continue processing messages without grinding to a halt. And that's going to be far better than having to just have your consumer go completely down because of one message that went wrong. We could have an application downstream that only cares about a subset of events in our source stream. Kind of alluded to this a couple of slides ago, but we could let that consuming application filter out what it doesn't want on its end. That's not really going to be ideal for a couple of reasons, though. That the application is going to have to maintain the filtering logic by itself. So let's say later on I'm writing another application that wants to apply the same kind of filtering logic. Well, now I've got to implement the same logic in this application too, and I'm maintaining it in 2 places. So that's kind of a maintenance problem over time. Also, if we've got more than one app that needs to filter events the same way, all these different applications, if they're doing the filtering on their end, have to read more data than they really care about so they can do that filtering, and that's inefficient. You're wasting network bandwidth, you're wasting processing time in your consumers. So instead, we can put a stream processor in the middle and let it do the filtering. Do that filtering once, emit a new output stream that contains only the events we want to filter for, and then any application that wants that filtered subset of the data just needs to subscribe to that new stream, not do any extra work. So as we're working with our streaming platforms, over time we're going to be connecting a variety of different systems, and it's not always going to be feasible to use common data formats across all these systems. And it's also not necessarily always going to be feasible to implement that translator pattern I showed upstream, where inside of my application, I've got some kind of an event translator that's turning it from the internal data model into what I want to produce to Kafka. I might have like some legacy app I'm afraid to change, or some third-party vendor app that I don't have access to the code for. So how can I get those communicating with other systems through Kafka events? Well, I can do that event translation in the middle with a stream processor instead to take the data coming from the input topic and then format it into that standard format that I want, that's going to be familiar to all my downstream stream processors and usable by any other applications that might want it in the future. And I can do that transformation again in one place. I only have to maintain it in the middle, and no extra burden falls on the consumers to do that translation to get the message format they want. All right, so now we've got applications producing events, applications consuming events, a bunch of stuff happening in the middle in real time. Now we need to think about how our events are going to be stored in the streaming platform and for how long. So a lot of use cases are going to be for ephemeral data, events that can be removed from the stream at some point in time once they're not of any value anymore, to preserve some state, stop from having to read and deal with stale data. So the solution for that is going to depend on what particular platform you're using. In Kafka, the brokers themselves are going to handle this cleanup based on the cleanup policy and the retention period that we set for a given Kafka topic. And like I said, because the underlying structure in Kafka is this immutable log, we can't just go delete things from the middle of it. So all we're going to be doing is the oldest events from that earliest part of the log, based on whatever my retention period is configured, the old events are just going to age out and get cleaned up in the background asynchronously. You do want to make sure you consider things like your potential reprocessing needs when you're considering how long you want to retain your data in Kafka. It's like I mentioned, if a consumer fails and needs to be able to reprocess events in order to return to the correct state, then you want to have enough runway to let it do that. You might have a use case where you want to have the ability to fully rehydrate some downstream database and get it back into a consistent state from the stream of events that's in Kafka. So you got to kind of consider what the half-life of value for the data in your topic is and take that into consideration when you're configuring retention. A lot of times we might have some streams that are representing like a snapshot of the state of something like a table in a database. Commonly we're going to see this with those keyed events where we've got a primary key of the event is representing a specific thing in the world or a specific record, and we're kind of keeping track of the latest information we know about that particular business entity that's related to these events. So we might need to process these events and to use them to determine the current state of that thing or that business entity. But keeping the entire stream of history of changes to that event might be too expensive. It might not make sense to keep all those over time. So how can we strike a middle there? How can I be able to maintain that virtual table as an event stream and be able to recreate my entire customer table downstream, for example, without needing to keep track of every single change that's ever happened to the customer? Well, I can do that in Kafka via this concept of compaction. So you heard us talk about a compacted topic in Kafka. That's what this is about. Instead of keeping all of the history for every event, for every key in that topic, what we'll do is we'll just keep the most recent version of a record we've seen for every given key in that topic, and then asynchronously go back and clean up all the historical events for that key. So you're never going to have a scenario where, let's say the last snapshot I had of my customer, John Smith, last change I had in my Kafka topic for him was a year and a half ago. John Smith's most recent record will still exist in that Kafka topic, just all the previous ones will have been gotten rid of. So that does give me the ability to still rehydrate my customer table downstream from this Kafka topic, but I don't have to replay years and years and years worth of events that I don't really care about anymore to do that. So it kind of helps us set a boundary on what the size of that topic will be. Our new boundary for the size of that topic really is a function of the number of unique keys in that data set. It's also a useful concept to understand compacted topics when we start working with Kafka streams or KSQLDB stream processing APIs. In K-streams, you've got this concept of a K-table, which is that state store it builds up. So you do on-the-fly aggregations or maintain a lookup table so you can join to other streams. You want that customer's view joined to a real-time stream of orders, like I was talking about before. Customers would usually be a K-table in that kind of scenario. So in your Kafka streams world, on the stream processing node itself, there's going to be a RocksDB cache that kind of helps those lookups be really fast and not have to go to the Kafka stream and replay a bunch of events to look up a particular customer. But that table is ultimately backed by a compacted topic in Kafka, so that if your KSQLDB or KStreams app fails, it can start back up and rebuild that state from the Kafka topic and get right back to where it was. We're going to have some use cases that might demand that we do store all of the events from an event stream indefinitely in their entirety. And that can get really big from a storage perspective. So how might we be able to do that? How you can achieve infinite retention is going to depend on the particular platform you're using. With Kafka, it comes available out of the box. The only real limit you have on what you can store in Kafka is how much disk and storage you got available. In Apache Kafka, the Kafka Improvement Protocol Kit 405, or proposal rather, Kit 405 is bringing tiered storage to Apache Kafka. It's out there in Kafka 3.6 on a preview basis right now. I think a couple versions, maybe later this year, will be production ready. Bringing the concept of tiered storage into Apache Kafka, which lets you use an object store like S3 to automatically tier out older events into cheaper blob storage, and then just leave a metadata reference to the Kafka topic. So, usually 9 times out of 10 stream processing use cases, you're looking most at the hot events that just came in. You're not really looking back into the deep history very often. So the expense of going to that colder object store to retrieve older events, you're not going to hit it very often. And when you do, you're willing to make that trade-off of performance for storage price. Confluent, we've got our own proprietary implementation of that that's actually available for production use today, both Confluent Cloud and Confluent Platform. Some of your other data streaming platforms might not natively have support for something like tiered storage, so other ways you might support this kind of use case would just be have some kind of a sync connector that takes events older than a certain point and just send them to like a database or S3 bucket for long-term storage. Finally, one really critical piece we want to consider is schema management. So being able to keep our data producers and data consumers fully decoupled from each other is really powerful, opens up a lot of new architecture options, but it also means we've got to establish really robust data contracts between those producers and consumers so they agree on what those events are supposed to look like. Schema evolution is a really important aspect of data management. Every data system has to deal with this some way, somehow. Just like how APIs evolve over time and you need to maintain compatibility with applications that might be relying on older or newer API versions, schemas are also going to evolve and they need to be compatible with applications that rely on older or newer versions of the schema. So how can I restructure or add new information to an event in a way that's going to remain, going to maintain some kind of compatibility with previous schemas that I've had in that topic? You've got to be really thoughtful about this. Different kinds of schema changes are going to introduce different compatibility challenges. Like, let's say I add an optional field to my payload in version 2 of the schema. That's going to be a fully backward and forward compatible change, meaning like producers can write events with or without the new field, and the consumers aren't going to care whether that field exists or not. But let's say version 3 of my schema removes a field that was previously a required field. That's not a backward compatible change. That is a backward compatible change, not forward compatible. So our consumers might have problems with it if they're still using version 2 of the schema. When I'm talking about a schema change being forward compatible, what I mean by that is if I have a consumer using the version 2 of the schema, they can still read of events that were produced using the V1 of the schema. And vice versa, if I have a schema change that's backward compatible, I mean the reverse of that. A consumer who's using version 1 of the schema can easily read events that are being produced by version 2 of the schema. So you can kind of start to see how we can quickly run into some problems if our producers just suddenly start producing events with a schema that's different from what our downstream consumers are able to read. So how can we deal with that problem? So like I mentioned before, Kafka itself doesn't care what the event payload looks like. It's just going to accept whatever binary data you throw in. So it's up to you to understand how that data has been serialized and what the structure of each record is going to be. So we need to add some kind of a schema registry in the middle that's going to help us with this. That's going to store the expected schema and serialization format for the messages in that stream and help us validate that any new events that are getting produced are valid and conform to that schema that's been registered for that topic. We can do that schema validation in 2 ways. One way you could potentially do it is on the server side. In Confluent Platform, we've got this notion of a broker-side validation, which you can watch the message being produced in the Kafka topic, make sure that it's been tagged with a particular schema, and if not, return an error back to the producer. You can also do this on the client side, where your producer application checks against the schema registry and uses the serialization library it uses to produce that message, make sure that the message content is valid and compatible with the schema that you're using before producing it to the broker and raising error otherwise. And Confluence serializers, if you've worked with Avro or JSON serializers or Protobuf, open source that most people use if they're developing for Kafka, use an Avro or Protobuf, take care of this for you. We've also got the Confluence schema registry to handle storing those schemas, which is available for free under the Confluence community license. Now, talking about evolving the schemas, like I mentioned, we've really got two fundamental scenarios. We've got compatible changes and incompatible or breaking changes. If I'm making compatible changes, it can be either forward or backward compatible, it can be both. But if there's compatibility, then I can evolve that schema in place, use the same topic, and within that topic, I might have records that contain events from the old schema version and the new schema version. And because I've got schema compatibility checks in my client and the schema registry, I can make sure that as I evolve that schema, I can enforce that I don't accidentally register a new schema that's breaking backward or forward compatibility or whatever I expect. We could take another approach to use dual schemas or dual topics and create version streams. And this is the approach that we're really going to use if we're going to introduce breaking changes that just are not going to be compatible either forward or backward with messages in the existing topic. So in this case, we create a second stream, we register the new schema for the second stream, and on the source side or the producer, we make it start emitting events in parallel, version 1 schema to the original topic, and version 2 schema to the new topic. And then over time, we start migrating our stream processors and our consumer applications to read from the version 2 topic. And then as we've got everybody transitioned off and we're not consuming from the V1 stream anymore, then I can shut that down, take the old producers offline, and we're only on V2 at that point. So that gives you an overview of some of the most common patterns we see for how to structure and maintain storage of events in Kafka or any other data streaming platform. Once again, really encourage you to check out the Confluent developer site to learn more. It's a really great resource. A lot more design patterns than the ones I talked about are available on there. Also, a lot of great just like mini training courses, little hands-on courses taking you less than an hour to complete, articles, blogs, really, really great wealth of information. Also, really encourage you to check out the Confluent community forum and Slack. Great place to ask questions, get help from other people out in the community. Lots of active Apache Kafka committers, not just Confluent employees, active on there as well, answering questions regularly. And lastly, if you want to get started playing with any of this, experimenting, and you don't want to take the time to figure out how to get Kafka up and running yourself, feel free to check out Confluent Cloud. We've got a $400 free starting credit for new signups. You can get in there and play around. The basic cluster here doesn't have any base costs associated with it, so you can leave that running for free forever and just start kind of experimenting and get more familiar with these concepts for yourself.
All right.
Thank you very much for coming out.
Thank you, Chris. Good. Keep that up for a minute in case anyone needs to get a screenshot of that. Any questions? I think we got a little bit of time for some questions before we jump into the last little bits. Yeah. Anyone have any questions for Chris?
I can see you thinking of one.
Anybody using Kafka currently, or Confluent, or using any of the kind of competitors? There's Rabbit. There's some others, or using anything that this might kind of solve some problems that or challenges, solutions that you all have. We'll kind of talk about. Yeah.
A little bit. We are using both Kafka, AWS, Flavor, MSK, and then Confluent Cloud. I leverage it in my machine learning pipelines because if I'm processing either real time or batch, I can throw things that I need to go and say, make a prediction. Leveraging my model, I can throw those to one topic. I can then have a processor in the middle, the consumer that's reading from that. I can go make predictions and throw those to another topic. And have multiple consumers go into applications, right, that I might be interfacing with for the business. So I use it all the time.
Anyone else? using it or have some thoughts on ways they might be able to use it. Okay, cool. Excellent. Well, thank you, Chris, for that. Hey, look, update. As we mentioned 2 months ago, we're back. CFP is still open for another week, 8 days, or 7 days and 4 hours and 46 minutes. You have the CFP. If you have, that is actually almost on the dot. So just for clarity and specificality, so if you have a talk you would love to give or kind of present that out there, go out. CFP's open. You can also get tickets at tickets.devopsdayskc.org. And if your company is looking at, they would be interested in buying a bulk number of tickets. I know a number of companies in the past have done, like they'll buy 10 or 20 tickets for all their engineers to show up, engineers and ops. We can work some deals and kind of find something that works for you all, including some options where you might actually be able to be listed as a company sponsor as well. So get your name out there a little bit more. So definitely kind of talk to me, or there'll be links on either one of those with questions if you have any questions around that. But yeah, tickets are open. Early bird is open for another, I think it's like 60 days, 45 days. And then prices will go up like 25%. So instead of $149.99, it's $199.99. We figured, like we're trying to sell used cars, and we'll just kind of put the nines at the end. Or if you think about it this way, we're going to run 4 nines. It's really three to four nines is how we're going to be doing our tickets. Actually, I need to make that a tweet. Yeah, I'll make that into a tweet. But yeah, definitely, we're going to be at the Madrid Theater. If you've never been there, it's a awesome venue. Definitely for at least for concerts, it's great. If you've been to weddings there, I mean, we're not going to be as snazzy as that, or we will. We'll see. But also, it's just a great spot. We're going to have a lot of different things going on. It's 2 full days. So check that out. And if your company wants to sponsor, there's a lot of opportunities for that too, in terms of getting a great way to recruit when you have a captive audience of engineers and operators and across the whole spectrum. It's like 70% of attendees in the past have been like senior engineers. So it's a great opportunity if your company's looking to get in front. So a lot of good opportunities open on the sponsorship side. So check that out. If you have any questions, you can definitely reach out to me, or you can check us out on that. Any questions on who all has been to a DevOps Days or DevOps Days KC in the past? The last one we did was 2019. Got to about a third of us. How many want to go? That should be. I see a lot more. Okay, almost 100% raising their hand. Okay, good. It's great. It's a good opportunity to not only network, but some really great talks every year. And I've been lucky to go to a lot of them over the years, and a lot of conferences as well. And DevOps Days conferences around the world are some of my favorite conferences to go to. The community aspect, the opportunity to learn kind of how things go. There'll be some talks in the morning, and there'll be these things called open spaces in the afternoon, which is literally you kind of propose, you have an idea, or kind of like we did here is we have this, hey, I'm thinking about this, I want to talk about this little thing, or I have a thing that I'm struggling with or thinking about at work, and you kind of pitch that at the conference, and a number of people kind of say, yeah, I want to go see that, and then in the afternoon, there'll be little kind of sections where you just go and you sit, and it's kind of open discussion amongst, and then I think we do 2 sessions of those in the afternoons, and those are almost as good as the talks because you really get a lot of good ideas, and I've seen some really great things come out of that. So it's a good time to connect, and we will have a convince your boss letter as well to convince them with hopefully not too much pleading to allow you to go, or a lot of pleading. Maybe we'll have different levels there. If you really want to be desperate, we can probably, ChatGPT is great for figuring those things out too. So, With that, yeah, just kind of finishing up. We got still a little bit of pizza left, some drinks, and that is it. Thanks again to Tech Systems for hosting. Chris from Confluent, it was great. And thanks to Confluent for food and drink. And thank you all for coming.